Hi, in this video we'll be going over the hydration of alkenes, presented in section 9.7. We viewed hydration of alkenes in a previous chapter through the process of acid catalysis. If we perform the acid catalysis on an alkene, the expected product would be an alkene carbocation. So, as shown, during acid catalysis, the reaction of H3O plus forms a carbon cation. Unfortunately, this is very unstable, so this will not occur. So for these reasons, we won't be using this. Since acid catalysis will not yield a product, hydrating via oxymercuration must be employed. As seen with an alkene, in this reaction the OH group will bond to the more substituted carbon in the alkene bond, with the hydrogen bonding to the less substituted position. This reaction will produce an enol, an alkene with an alcohol group. This enol will quickly be tautomerized into a ketone under acidic conditions. Let me show you an example. So, for oxymercuration, we will use mercuric sulfate and water. The alkene will react with the mercuric, resulting in an enol. The enol solution will already contain acid H3O due to the presence of H2SO4 created from the SO4- in the first reagent. Tautomerization will now occur on this enol to produce a ketone. Side note, tautomers by definition are constitutional isomers that are in equilibrium in a solution. So, moving on. Alright, so let me show you the mechanism for this reaction. Now, I'll go over the mechanism. So, the reaction activates the alkene toward nucleophilic attack, and then forming a mercurinium ion. Following is the mercurinium ion. The mercurinium ion is then attacked by water, followed by deprotonation. So our water is attacked, and then deprotonation. Under these acidic conditions, hydrogen replaces mercury, forming an enol, but also forming a resonance structure. Alright, the compound formed is an enol. Acidic conditions rapidly convert the enol to a ketone. It should be noted that the enol is unable to be isolated. Alright, let's go over some examples. So with these examples, take a second and try to solve these on your own. Pause the video if needed. Alright, so now that you've worked through it, or if you're having issues, let's work through this together. So first, because of the mercury, we're going to form an enol. So, our enol, which then is going to react with our H2SO4 and our water to form a ketone. Alright, so for part B, it's very similar. A formation of an enol, alright, which is then reacts with the H2SO4 because of the acidic conditions. Would otherwise form a ketone. Do that. Alright. It's pretty straightforward. Just try some practice problems and you should get the hang of it. Next, we will discuss the Hydroboration-Oxidation of Alkynes. So, like previously discussed, oxymercuration, then acid-catalyzed tautomerization process synthesizes a ketone. The anti-Markovnikov hydration of alkenes results in an aldehyde. The two reagents used in succession are BH3, THF, or tetrahydrofuran, and H2O2 and sodium hydroxide. Respectively, this process involves the conversion of an enol into an aldehyde, but in basic conditions are opposed to the acid-catalyzed tautomerization used in the last topic. It's very similar to that of the use of an acid. So, under basic conditions, you'll have an aldehyde. You still have a formation of an enol, but the end result will be an aldehyde. So we'll go over the mechanism to show you a little bit better of how this works. So let's get into our mechanism of a hydroboration-oxidation of alkenes. We have our alkene forming an enol, which is then turned into an aldehyde because of the basic conditions. So for the mechanism of our enol, we have a proton transfer from the hydroxide taking a hydrogen, then forming an enolate ion. The enolate ion reacts with water as it takes a hydrogen from a water. It reacts with the water, taking a hydrogen, then forming an aldehyde. So let's move on and show you some examples for this so you guys can practice. Alright, so let me show you the example. Alright. Now I'll give you a second to try to solve it on your own. So I've already worked ahead to solve the problem. So to keep in mind that for the basic reaction, it's going to form an aldehyde as an end product. But it's also an anti-Markovnikov position. So first, formation of an enol. The hydroxide deprotonates the hydrogen from the oxygen. Following after is the resonance structure. It's reacting with the water. Our carbocation takes the hydrogen and forming aldehyde. This concludes chapter 9.7.